right? So a little bit more about examples on Faraday's law. I mean, you can produce, you can create induction with, I mean, you have what? Epsilon induced is minus d phi magnetic by dt. So phi magnetic is the integral of b dot ds, the integral over the surface. So how can you change the phi magnetic as a function of time? You can change b itself. Let's say you have something else producing b, and you can crank it up and down or whatever. You can change the area, and you can change the angle between the two. What we've done so far is we've given examples where we change the area. An example where you're changing the area by pushing the bar this way, and you can change the angle by causing the loop to spin. Okay, how can you? What else can you do to change the area? Let's say you have, take this example for you have a square loop like that of side L, right? And so it's a square loop, side L, right, or side A, and this is being driven at speed v into a uniform magnetic field like that, B, okay? Okay, and you'd like to, as when this enters the field, you're going to see that the area of this loop sitting inside the field is going to grow until we get to this point where it continues to grow but at a different rate. So this is a very interesting problem in that now let's say we have the loop like this, right? And the loop has entered the field a little bit, right? And how do we now parameterize this, let's say it is entered here, okay? This part of the loop is inside the field. Pause for a minute now and see if you can find out A, which direction the current will flow in, and B, what is the magnitude or is the value of the EMF induced as you do this, okay? So, this is a square loop, the angle is 90. I'm going to pause for a minute, let you pause the video for a minute and see if you can come up with this. All right, so the flux is increasing in the forward direction this way. We need a magnetic field that is induced so that it is reducing, it's opposing the change of the flux. So this is B induced, right? And this guy is B external over here, right? So what we need now is as this goes in, we have an induced magnetic field coming out of the board, and for that to happen, the current must flow in this direction in the loop. So this is I induced. But now what is the value of epsilon induced, right? Let's say this goes in distance x here, and because this is square, this is x as well. The area of the part that is in the loop is given by, well, 1/2 x times x squared times 2 is just x squared. So we have now phi magnetic equal to, well, field is uniform, no need to integrate, which is B times A, bx squared, right? And d phi by dt, so epsilon induced magnitude-wise is d phi by dt, okay? And that's equal to d by dt of bx squared. And what that is equal to, well, you can say this is, again, chain rule, d of bx squared by dx times dx by dt, and that's equal to 2bx and dx by dt, that's just v. And that's your expression for the induced EMF. If you want the current, let's say that the loop has resistance R, and you say that I is that value, or the current in the loop is equal to 2bxv over R, okay? Let's say this thing has resistance R, okay? Then the induced current is going to be given by that, okay? Another example you can look at, okay, is, we've done a few of these so far, and I'll give you some tips as to how to, construct ways whereby you can, let's say, have the same square loop again, okay? And this loop now is again of length L. It is sitting in a magnetic field like this, right? And okay, this is uniform magnetic field. The field is not changing, right? Now, what you're going to do is look at, okay, so this is uniform magnetic field, right? And what you're going to do now is grab this loop here and there, pull it this way and this way at speed v, and in this fashion, so you've seen examples whereby you change the area, you could change the direction, you can change the field. Now what you're going to do is, this is a collapsible loop, you're going to zip this out, right? And as you do this, this is going to come down, and this is going to come down, and the loop is going to collapse. So how are you going to parameterize this change in the area so that gives you epsilon induced equal to d phi by dt? Okay, again, we're looking at the magnitudes. You know, phi magnetic is b times a. How is the area changing on you as you do that? So I'll give you some tips as to how to do that. You are going to consider, you know, that this loop has collapsed this far. Okay, consider it here, and then see what you can do to parameterize the area. I mean, the area is changing, for sure changing. How is the area changing? You have this business that started at L, whatever the length was here, and now you have it, you know, changing by this much. What is the new length here? How does it relate to y? And you know, can you find an expression for the area in terms of the speed, or of changing the area in terms of the speed at which you collapse the coils, right? Collapse the loop. Another example is, let's say you have a big solenoid like that, and mutual inductance calculations can be pretty tricky, right? Because let's say you want to calculate and you have another little solenoid inside. Okay, so this is object 2 and this is object 1. Okay, I mean, if somebody was to ask you to calculate the mutual inductance phi in 1 from 2, phi in 1 from 2, phi in the big object from the little object, that's a bit of a messy calculation, no? Because we're talking about ideal solenoids, you say you have to be long and whatnot, but the problem is that, let's say the field looks nice and clean inside here, right? The field due to this little solenoid, and you have the field due to the big solenoid too, but the field due to the little solenoid looks nice and clean, but you have, you know, it goes like this, it goes around like that, and then, you know, how do you calculate? You see, if you calculate the flux in 1 from 2, it's a bit of a mess. Just like trying to calculate the, say people try to do the calculation of the mutual inductance between, let's say you have a ring of current and another ring here, like two conducting loops, one inside the other, and they say they want to calculate the mutual inductance between the two. Well, if this is object 1 and this is object 2, and you want to calculate the flux in the big one from the small one, that's a mess, because what does the field look like from the small one? Well, it's a perfect, it's an ideal, you know, it's a textbook dipole. And how do you calculate? That's a bit of a rough calculation, right? So what you could do is say that, okay, well, I can find the field at the center of the ring, which we know how to do. You know, we calculated that in the class before we went away, and we know the field inside. We know the field due to this circle, to this, let's say you have, you create current I here, you calculate the field from this at the center of the loop. You say this, you know, one of the problems is that if this gets big enough, you know, we have a problem in that the field is not uniform over, so you have to integrate, and the expression for the field over the smaller circle, as it gets bigger, becomes really complicated. So you can only approximate. You can say that, I can approximately say that, you know, this loop is small enough so that the field doesn't change appreciably in it, and it has little area A, so the flux in it is equal to B, so I'll say that phi in 2 from 1 is equal to B1 at the center times area of 2. Area of 2 is small enough so that B is uniform over it, and that is kind of doable, right? And then you can say that that divided by I in 1 is going to give me the the mutual inductance in this case. So M into from 1 can be given by that. Okay? Right? So going back to this, you have a big solenoid of, let's say, number of turns N1, and this is number of turns N2. This has area A2, and this has length L2, while the big one has length L1 and area A1, which we are not likely to use. Okay, I want to calculate the mutual inductance. So let's say we tell you that there is current running in 1, right? I in 1 is equal to I naught sine of omega t. What would the current running in 2 be? Right? How does that show up? How do you calculate that? Well, what kind of induced what's the epsilon induced this is pickup coil, let's say, okay? You want to measure the epsilon induced here. You have current going through, current I1 going through this, and that will create a magnetic field, B1, which is going to be everywhere in this space, right? So let's say it goes this way, and over here, it's going to overlap with where the little solenoid is. And now the question is, you're trying to ask is, what is the induced EMF in the second coil, in the pickup coil epsilon 2, if the current in 1 is given by that. Right? So we'd like to now calculate the mutual inductance. And mutual inductance is phi in 2 from 1, phi in 2 from 1, divided by I in 1. Okay? So pause for a second. See if you can find this mutual inductance M in 2 from 1. Pause the video and see if you can find M21 as phi in 2 from 1 divided by I1. All right, so what is phi in 2 from 1? Phi in 2 from 1 is, take it step by step, is equal to the field from 1 multiplied by the area of 2, we're not integrating, multiplied by the number of turns N2, okay? And divided by I in 1. And that is equal to what? B in 1 is equal to mu naught, okay, times N1 times I1 multiplied by A2 multiplied by N2, because we have flux per turn is B times A. You have so many turns, you have N2 and N2 turns divided by I1, and that gives you the mutual inductance. Okay, so epsilon in 2 from 1, epsilon in 2 from 1 is equal to so this is, you can say that is equal to M21 times di1 by dt, right? All right, cool. Let's pause here, and we'll continue in a bit.